Speaker, whom we will listen to with great attention, is Pollack from the University of Georgia. Please go ahead.
Okay, sorry everyone for the delay there. So thank you for the organizers for the invitation to speak here. I'm going to be talking about some joint work with my PhD student, Matt Just. So there were some other things that were kind of hinted at in the abstract, but in the interest of time, I'm going to focus on just one theme of problems, which is a subject that I'm calling comparative order theory. So let A and B be integers that are not 0 or plus or minus 1. And the questions we want to ask are questions of the following. How does the order of A mod P compare to the order of B mod P as P varies over the primes? Okay, so the maybe most famous question in this direction was a question that has come to be known as Erdős' support problem. So Erdős' support problem is the following. Take integers A and B, not 0 plus or minus 1, for which, when is it the case that the order of A mod P and the order of B mod P are actually the same for all but finitely many primes P, or let's even say for all primes P. And the reason it's called Erdős' support problem is that if you think about what the order means, this is equivalent to asking, when is it true that for every positive integer n, A to the n minus 1 and B to the n minus 1 have exactly the same set of prime divisors? And that's what we'll call a support. Okay, so it's interesting that Erdős posed this question in 1988 because already in 1960, Schinzel had answered the question. And it turns out that there's a very simple condition. The condition is just that A has to be equal to B. Okay, so this is a very strong condition. It actually enforces equality. And in fact, Schinzel's proof shows that you get equality here, even if you don't assume that they're equal for all primes P, but just that they're equal for all but finitely many primes P, or even something weaker, if you assume they were equal for all primes except a Dirichlet density, except a set of Dirichlet density 0. So I'm going to very quickly sketch the proof of this. So here's Erdős on the left and Schinzel on the right. So I'm going to sketch the proof of this, although at some point I'm going to kind of farm out the rest and say if you want to know the details, you should ask your resident algebraic number theorist. But I'll get you started. So here's one way of proving this fact that A has to equal B if the orders are the same for all primes P. So let's suppose that the orders are the same for all primes P, and let me let K be any positive integer. Then take any prime 1 mod K. I claim that A to the P minus 1 over K is 1 if and only if B to the P minus 1 over K is 1 mod P. And well, it's easy to see that that's true because when is the left-hand side congruence true? It's true exactly when the order of A divides P minus 1 over K. But the order of A is the same as the order of B, so that's the same condition for the right-hand congruence to be true. And now, if you've thought at all about conditions for prime splitting in Kummer extensions, you'll see why I wrote this kind of funny looking thing. The condition that P is 1 mod K and A to the P minus 1 over K is 1 mod P, that's exactly what you need for P to be a split completely prime in Q adjoins zeta K, Kth root of A. And now this equivalence tells me that the primes that split completely in Q adjoins zeta K, Kth root of A are the same as those that split completely in Q adjoins zeta K, Kth root of B. And we know this for every K. And here is the part where I'm going to say, ask your favorite algebraic number theorist friend. This implies that actually A has to be the same as B. Now, I'm not going to prove that, but just as a plausibility argument, this is to convince you this is giving us a lot of information. Let's just take K equals 2. Then the left-hand extension is just Q adjoin root A because zeta 2 is a rational number. The right hand is Q adjoin root B. Knowing those are equal tells you already that A and B have the same square free part. And the claim, which you need a bit more algebraic number theory for, is that, yeah, if you really know these are equal for every K, not just K equals 2, then that forces A to be equal to B. Okay, so a variant of this proof will prove something that you can easily convince yourself is a bit stronger. If you just assume that the order of A mod P divides the order of B mod P for all primes P, or for all primes P up to a density 0 set of exceptions, then you can conclude that A is a power of B. And then using this both ways, you can get back our conclusion that A equals B whenever the orders are equal. Okay. So I want to talk about some problems which are in a slightly different vein. So let's consider this, or a similar looking question. So let's consider order of A mod P equaling order of B mod P. But let me now ask if this holds for all primes P, but just for infinitely many primes P. And that should be a much weaker condition on A and B. That should happen quite often. For instance, if you're familiar with the kind of reasoning that goes into the prediction of Arden's primitive root conjecture, then you would suspect that for generic values of A and B, suitably generic in some sense, the order of A and the order of B should both be P minus 1 infinitely often. And then, of course, they're equal. Now, of course, if A is a square or something like that, then you're not going to get the order of A to be P minus 1 on the nose. But you can still use the methods that go into the GRH conditional proof of Arden's conjecture to show that if you take any A and B that are integers not 0 or plus or minus 1, then there are, in fact, infinitely many primes P where these two orders are the same. And, well, under GRH, not just are the same, but you could get them to be the same and bigger than a certain constant times P. But what I want to talk about in this, what I want to focus on in this talk are, what can you prove if you don't assume GRH? And it's a beautiful theorem of Schinzel and Wojcik that you can still get the orders are the same infinitely often, unconditionally. So part of the reason for this talk is kind of to advertise this theorem, which I think should be better known. So A and B, again, integers not 0 or plus or minus 1. The claim is there are infinitely many primes P for which the order of A and the order of B mod P coincide. And let me try to convince you of this in the special case when A equals 2 and B equals 3. So I'm going to say we're going to look at primes that divide this expression 2 to the L minus 3, where L is a prime that I'm going to vary. Now, if I look at 2 to the L minus 3, well, by Fermat's little theorem, 2 to the L is the same as 2, so 2 to the L minus 3 is negative 1 mod L. And negative 1 is not the same as 1 if L is an odd prime. So 2 to the L minus 3 is not 1 mod L. Well, if 2 to the L minus 3 is not 1 mod L, it means there's a prime that divides 2 to the L minus 3 that's also not 1 mod L. So let me pick that prime and call it P. And I claim that I've just discovered a P for which the order of 2 and the order of 3 coincide. Why? Well, P divides 2 to the L minus 3, so 2 to the L is 3 mod P. And I just said that P is not 1 mod L, so L doesn't divide the size of the multiplicative group mod P. Well, if L doesn't divide the size of the multiplicative group, raising to the Lth power is an automorphism of that group, and so 2 to the L and 2 have the same order, but 2 to the L and 3 have the same order because 2 to the L is 3 mod P. And so I found a prime P where the order of 2 and the order of 3 are the same. Now, you might say I'm done because I can just vary L, but you have to be a bit careful here because I need to know that I really get infinitely many different primes P as I vary L. It would be bad if I just got the same prime P over and over again. And one way to work around this difficulty is not to use all primes L, but just to use L from a certain sequence. And we're just going to use L from a sequence where the numbers L minus 1 pick up more and more factors. So let me say it in a down-to-earth way and just say I'm going to choose my sequence of primes L so that the nth L in my sequence is 1 mod n factorial. And then I claim that this proof really does work. And the way to see that is I'm going to argue that any prime that is discovered as a divisor of 2 to the L minus 3 at some point in this process is discovered only finitely many times, meaning finitely many L. And because I have infinitely many L's to play with, if I only see repeats, if the number of repeats I see for any prime P is finite, I have to see infinitely many primes P. So to see that any prime that's discovered is discovered only finitely many times, let P be a fixed odd prime. And let me argue that P is not going to be discovered as a divisor of 2 to the L minus 3 if L is large enough in my sequence. And the reason P is not going to be discovered as a divisor of 2 to the L minus 3 if L is large enough in my sequence is that, well, if L is large enough in my sequence, remember, I chose my L so that L minus 1 is picking up more and more factors. The nth L is such that L minus 1 is divisible by n factorial. So for all large enough L in my sequence, P minus 1 will in fact divide L minus 1. And if P minus 1 divides L minus 1, then you can just compute 2 to the L minus 3 mod P. You'll find that it's 2 times 2 to the L minus 1 minus 3. And P minus 1 dividing L minus 1 tells me that this just works out to be -1. So 2 to the L minus 3 is -1 mod P. In particular, it's not 0 mod P. So P doesn't divide 2 to the L minus 3. Okay. So this completes this nice argument of Schinzel and Wojcik that there are infinitely many primes for which 2 and 3 have the same order mod P. Okay, so far what I've said is work of others. I want to focus on the last part of this talk on the new question that Matt and I asked. So we replace the equal sign with a greater than sign. So the question is, take A, B, integers not 0 plus or minus 1. When is it the case that the order of A mod P is bigger than the order of B mod P for infinitely many primes P? Now, again, if you're willing to assume GRH, you can get an exact answer to this question. So I'm going to say the pair AB is order dominant if this holds. So the order of A mod P bigger than the order of B mod P for infinitely many P. If you assume GRH, you can completely characterize order dominant pairs. And what you find is that AB is order dominant unless A is a power of B. So that's a beautiful and complete characterization, but it assumes GRH. And it would be interesting, again, to ask, what can you prove in this problem if you don't want to assume GRH? Okay, so let me give you an unconditional proof that the pair 2, 3 is an order dominant pair, that the order of 2 is bigger than the order of 3 mod P for infinitely many P. And for this, what I'm going to do is I'm going to look at P's that divide this peculiar expression 2 to the n factorial minus 3. Now, as long as n is at least 3, 2 to the n factorial minus 3 is going to be -3 mod 8, which means that this Jacobi symbol 2 on 2 to the n factorial minus 3 is -1. And the fact that that Jacobi symbol is -1 implies there's a prime that divides its denominator, where 2 on P is also -1. So I can find a prime dividing 2 to the n factorial minus 3, where 2 is not a square mod P. And I claim that I've located a prime P for which the order of 2 is bigger than the order of 3. Now to see that, let's notice that since 2 to the n factorial is 3 mod P, 3 is certainly in the subgroup generated by 2. I've written 3 as a power of 2. But in fact, I've written 3 as an even power of 2, and so 3 is a square mod P. But 2 is not a square mod P. That was how I chose my P. And from these two things together, you see that the subgroup generated by 3 is inside the subgroup generated by 2 and can't be the whole thing, because otherwise 2 would be a power of 3, which would make 2 a square since 3 is a square. So that means that 3 generates a proper subgroup of the subgroup generated by 2. And so if you compare the orders of the subgroups, you get that the order of 3 is smaller than the order of 2. Now, there's still exactly the same issue I mentioned before, which is, okay, this gives me a recipe for constructing P's that I want. How do I know that infinitely many different P's arise this way? And that's proved in exactly the same manner as before. You show that a given odd prime P will divide only finitely many of the numbers 2 to the n factorial minus 3. The point is that eventually P minus 1 will divide n factorial, and then 2 to the n factorial minus 3 will be congruent to -1 mod P. It won't be 0 mod P. Okay, so this is a proof that there are infinitely many primes P for which the order of 2 is bigger than the order of 3. And again, you might want to generalize it, and you might hope that maybe you could prove something like the Schinzel-Wojcik result. Maybe you could prove unconditionally that GRH conditional classification of order dominant pairs. But unfortunately, I don't know how to do that. And this argument that I've given, which is really due to Banachak in another context, it's promising, but it doesn't generalize as far as you might like. And you can already see there's going to be a problem, because in this proof, all of the P's that we found were such that 2 is a non-square mod P. So if we had been trying to run this argument with a number A instead of 2, and if that number A were actually a square in the integers, then we'd be out of luck, because there'd be no way of finding primes P for which A is not a square mod P, and so no hope of establishing the order dominance of a pair of the form AB. So, okay, undeterred, you can ask, We can't hope that this argument proves everything we'd want to prove, but you could ask, well, what have we proved? And one of the first things Matt and I do is try to write down a fairly general set of cases where we could get this to work. So I'll run through this quickly. I don't expect you to memorize these cases or anything, but I just want to give you the flavor of some of the things we could prove. So if A and B are odd positive integers, then we could prove that the order of A is bigger than the order of B infinitely often if either of these two Jacobi symbols is -1. We can prove that the pair 2B is order dominant for every odd positive B. We can prove the pair A2 is order dominant for every odd positive A that's not 1 mod 8. And we have this result if you have co-prime positive integers with B bigger than A to the 4th, then minus AB is order dominant. So this last case is maybe of interest because the pairs in this case are of opposite sign, or the numbers in the pair of opposite sign. Okay, so these are just some of the things we could prove by this method. And just to give you maybe an even more concrete illustration of what you can show, if you take two distinct primes from the list 2, 3, 5, 7, you can resolve the question for any pair like that. Okay, so that still leaves a lot of things we can't do. And let me point out one pair that I don't know how to do. I don't know how to handle the pair 17, 2. So this isn't the only pair that I don't know how to handle, far from it, but for some reason, I kind of latched onto this. So let me tell you maybe why this is such a frustrating thing for me to say I don't know how to do. It's actually straightforward to cook up primes for which the order of 17 is bigger than the order of 2. You can argue, similarly to how we argued in previous slides, that if you look at this expression here, 2 times 17 to the 6k plus 4 minus 1 over 7, then this will always have a prime divisor p with 17 on p being -1. And then the same kind of argument we saw on the previous slide will show that for this prime p, the order of 17 is bigger than the order of 2. So all you have to do to finish off the proof is to show that as you vary k, you pick up infinitely many different primes p. And this seems pretty hard. So it doesn't seem like the sort of thing that should be hard, but at least the way I've been thinking about it, it actually does seem hard. I don't know how to do this. Okay, so let me maybe try to end on a more positive note. So I'll mention a few other things we can prove. So quadratic reciprocity is not the only game in town. If you take higher number theory courses, you'll see higher reciprocity laws at some point maybe. And using the cubic reciprocity law, Matt and I were able to prove the following theorem. If you let a be an integer that's not a multiple of 3 and whose square is not 1 mod 9, then the pair a -3 is order dominant and the pair a3 is order dominant. So for example, you could take a to be 4, and you'd get that the order of 4 mod p is bigger than the order of 3 mod p for infinitely many primes p. And yeah, the proof of this uses cubic reciprocity. And the reason we have a -3 here is maybe not surprising because cubic reciprocity is somehow about the field q adjoint root -3. Now this is a kind of limited result. For instance, the only b's, the only second elements of the pairs I'm considering are -3 and 3. It would be nice to do more with higher reciprocity laws, but I don't know how to do that. Okay, so the last thing I want to talk about is a result which is more in the vein of analytic number theory. And I just want to set it up. I'm not going to try and go through the proof. So I don't know how to prove that the pair A2 is order dominant for all A that are not a power of 2. That's what GRH would predict. But we can at least prove that the pair A2 is order dominant for almost all positive integers A. And by almost all here, I mean all except from a set of density 0, asymptotic density 0. And the proof of this uses prime divisors of Fermat numbers. And so I'll give the idea quickly and say the analytic result we prove, and then I'll end. So it's well known that if you look at these Fermat numbers, that any two are relatively prime, so they're pairwise relatively prime. It's also easy to see that if you take a prime divisor of 2 to the 2 to the n plus 1, then the order of 2 mod p is 2 to the n plus 1. And another fact that's well known, and I've put the proof on the slide, but I'll just state the conclusion in the interest of time, is if you take a prime that divides the nth Fermat number and n is at least 2, then p is 1 mod 2 to the n plus 2. So 2 to the n plus 2 divides p minus 1. Now, suppose you know for a particular integer a that there are infinitely many Fermat numbers for which this Jacobi symbol is -1, a on Fn is -1. Then I claim you can quickly convince yourself that a2 is order dominant, that there are infinitely many primes p for which the order of a is bigger than the order of 2. And why is that? Well, if a on Fn is -1, choose your p dividing Fn with a on p being -1. Then the order of a mod p, because a on p is -1, that forces the power of 2 that divides the order of a mod p to be the same as the power of 2 that divides p minus 1. But I just said that the power of 2 that divides p minus 1 is at least 2 to the n plus 2. So that forces 2 to the n plus 2 to divide the order of a mod p. On the other hand, p divides Fn, so the order of 2 mod p is only 2 to the n plus 1. So the order of a mod p is divisible by 2 to the n plus 2. The order of 2 mod p is just 2 to the n plus 1. That means the order of a mod p is bigger than the order of 2 mod p. And you pick up infinitely many different p's that way because the Fermat numbers are relatively prime, and we're assuming there are infinitely many different Fn's like this. Okay, so what is it we prove? Well, using some basic analytic number theory, the most difficult result is the Brun-Titchmarsh inequality. We prove that this condition that there are infinitely many Fermat numbers like this holds for most values of a. And in particular, for almost all values of a up to x, there are infinitely many Fermat numbers n, with a on Fn being -1, which means that the pair a2 is order dominant for almost all a. Okay, so I will go ahead and end here and just say, if you have ideas for how to go further, in particular, if you have any ideas on how to handle this thorny case that I got stuck on, please let me know. And thank you for your attention.
Thank you very much, Paul. Do we have any questions for our speaker? Yes. In the Q&A, Andrew has a question. Actually, Andrew, you can ask it. You can ask it.
I can read the question.
Okay.
Yeah, so Andrew asks if I can prove that the set of ratios, the order of 2 mod p divided by the order of 3 mod p with p prime bigger than 3, if that's dense in 0 infinity. And that's an interesting question. I have to think about it. I'm pretty sure the answer is no, I can't prove that. One question that I was thinking about, well, yeah, under GRH, I think this is actually maybe a special case of something that's in a paper of someone I cited earlier in the talk. But unconditionally, it seems very difficult. I mean, yeah, I'll say that. Yeah, I think under GRH, I believe it could be done under GRH. I'm not going to swear that I know how to do the details right now.
Other questions for Paul? If not, thank you again for a very lovely talk. And